Okay, this section we're going to do is mechanism of reaction and of catalysis. It's on page 64 of your textbook. Now, catalysis has to do with using catalyst in a reaction, and we know that catalyst speeds up a reaction. Okay, so we're going to see how that happens and how the reaction changes when you change temperature and concentration and all of those, and how it affects rate of reaction. Right, now before we start, let's just do some revision. Now you remember activation energy, it is the minimum energy required for a reaction to take place, and it is basically kinetic energy. It's a certain amount of kinetic energy every reaction has, and any molecule that needs to take part in that reaction needs to have that minimum energy, which is called the activation energy. So any molecules that don't have enough energy, or they don't have the activation energy, they won't be able to take part in the reaction. Now you remember this graphs we did here, which is potential energy versus course of reaction. This graph shows you whether the reaction is exothermic or endothermic. And it also tells you the activation energy of a reaction, which is always from the reactants, which is the beginning of the graph, to the highest point or the maximum part of the graph. So this distance from the highest point to the beginning of the graph, this is activation energy. Now, the higher the activation energy, the more difficult it is for the reaction to happen. So the reaction will happen slower. The lower the activation energy, it means that more particles will be able to have enough energy or kinetic energy to take part in the reaction, so they will be able to collide effectively and they will take part in the reaction. So the lower the activation energy, the more easier the reaction is and the more faster it will happen. Now, in real life, when we have a system or a reaction, some of the molecules that are there, or some of the reactants, will have extremely low kinetic energy, which means their kinetic energy is going to be less than the activation energy, and they will not take part in the reaction. Then you will have, on the other end of the spectrum, some molecules or some particles which have very high kinetic energy, so they will move very quickly and collide much more. And because they have very high kinetic energy, they will have more energy than the activation energy, so they will take part in the reaction. But in real life, you will have most molecules which have in between. So they will not have too high or too low energy. They will have a moderate or like a medium amount of energy, and that is going to be the average energy. So most molecules will have an average amount, not too high or not too low kinetic energy, and depending on the activation energy of the reaction, that will depend on whether they take part on the reaction or not. Now, we have a graph which is called a Maxwell-Boltzmann distribution curve, and this graph tells us the fraction or how many molecules actually take part in the reaction, and how many have enough kinetic energy and how many don't have enough kinetic energy. Now, this curve, it is fraction of molecules with a given kinetic energy versus kinetic energy of molecules. Now, please do not mistake this Maxwell-Boltzmann distribution curve for a potential energy diagram. Potential energy diagram is what you have seen before, even in grade 11. It is telling you the activation energy of the reaction, is telling you delta H, whether the reaction is endo or exothermic. And the Maxwell-Boltzmann distribution curve is not a graph which tells you if something is exo or endothermic. It is completely different. It's not the same thing. So there's the two different ones. Please do not mistake this one for this one or the other way around. So this one here tells you the fraction or the amount of molecules that have a certain amount of kinetic energy, and on the x-axis it has kinetic energy of molecules. So it's completely different to this potential energy diagram one. Now, this Maxwell-Boltzmann distribution curve actually tells you how many molecules will take part in the reaction, because they will have enough kinetic energy which is greater or equal to the activation energy. Now, if you look at this curve, can you see it is increasing until it reaches a maximum, which is at T1, and then afterwards it decreases. And then you have this dotted line here, which stands for or corresponds to activation energy of the reactant. So anytime you see this curve, you will always see a dotted line, and that dotted line is always activation energy. Now, if you look at the left of this activation energy line, which is the white part of the graph. This part of the graph corresponds to all of the molecules, or the number of molecules that don't have enough energy to react. So which means if they don't have enough kinetic energy, they are not going to collide, so they will not be able to take part in the reaction. So all of the molecules, which is the white part of the graph, on the lower end of the graph, which is the lower values, those are the molecules that don't have enough kinetic energy. Then if you come on the right hand side of the graph, which is on the right hand side of the activation energy, can you see this blue part of the graph? This blue part corresponds to all of the molecules that do have enough energy to react, and because they have enough energy, it means it will be greater than the activation energy, so they will actually react and they will actually take part in the reaction. So again, everything on the lower part of the graph with lower values, those are the ones that's not going to take part in the reaction, and everything that's colored in blue, they will have enough energy and they will take part in the reaction. Now, can you see the difference? There is so much space here, or so much of molecules that are not going to take part, and this blue part is so small compared to this part, which means most of the molecules will actually not even take part in the reaction. And this is how it looks for most kind of reactions. Most reactions, only a small fraction of this graph or of this molecules will take part in the reaction. Now, the way that we get the amount of molecules is by the area under the graph. So remember, even in physics you do area under the graph. So same here, the area under this curve here, which is the white part, is all of the molecules that do not take part in the reaction. So the area under this graph corresponds to the number or the fraction of molecules which do not have enough energy. Then the area under this part, which is the blue part of the graph, this corresponds to all of the molecules that will take part in the reaction, and this part will always be less than this part here. Now, there's a few things that you need to remember about this Maxwell-Boltzmann distribution. The first thing is that this graph will always increase. It's not going to go through the origin, and that's because if it goes through the origin, it means you're going to have molecules that have zero kinetic energy, and in no circumstance are you ever going to get molecules with zero kinetic energy. All molecules will have kinetic energy. Even if they have little bit and they don't take part in the reaction, they will still have kinetic energy, whether it's a lot or a little. Right, another thing to remember is if you look at the right hand side of the graph, which is where the molecules actually will react, can you see that this graph is never ever touching the x-axis? It's just carrying on above it, parallel to it, but it's not touching it. And that's because if it touches it, it means you're going to have molecules that have no kinetic energy, or molecules that are not taking part in the reaction. So this part of the graph will never ever touch the x-axis like an x-intercept, because you will never have molecules that don't take part in the reaction. There will always be some molecules which take part in the reaction. Okay, another thing to know is where you see this peak of the graph, which is at T1, which is the highest part of the graph. This corresponds to the average kinetic energy of the molecules in that system, which means most of the molecules, because it's a peak, most of the molecules in the system or in the reaction will have this temperature, which corresponds to T1. And in this case, it just happens that most of this, which is at T1, will not take part of the reaction. So that just shows that only a small fraction of molecules actually take part in the reaction. Now, if we take this Maxwell-Boltzmann distribution curve and we flip it over on the side, it will look like this here. Can you see here? You have the Maxwell-Boltzmann distribution curve, and now it's the other way around. You flipped it over, and can you see now the activation energy is going to be here at this dotted line. Now, if you compare this to a potential energy graph, which is the one that shows whether something is exo or endothermic, the activation energy, which is from the reactants to the highest point, this distance here, will always correspond to the activation energy on a Maxwell-Boltzmann distribution curve. So this is just something not so important for you to know, but just so you're aware of it, the activation energy on a Maxwell distribution curve and on a potential energy diagram will correspond to each other if you flip the other curve around. Okay, so now that we know how a Maxwell-Boltzmann distribution curve works, let's look at how the reaction or the curve or the graph will change if we change the temperature. Now, you already know from theory that if you increase temperature, the reaction will go faster, or the rate of reaction will increase, and that's because higher temperature means more molecules have kinetic energy, and then they will collide effectively, and then the reaction will happen faster. Now, if we look at this graph, which is showing us the normal or the original graph for normal temperature, and the difference in how the graph will be if you increase the temperature, this is what you're going to get here. Now, the red graph, which is showing T1, is the original graph, which is the graph when you were just using normal temperature. And then the area under the red graph, which is this blue part, this corresponds to all of the molecules that have enough kinetic energy, and all of this molecules with the blue area, those molecules will take part in the reaction. Now, if you increase the temperature of the reaction, more molecules will have enough energy, which is greater than activation energy, and more of them will take part in the reaction. Now, when you heat up a reaction, you are heating up every single molecule, so every molecule is going to have more kinetic energy, even the ones that have less kinetic energy. So because you are increasing the temperature or the kinetic energy of all the molecules, can you see now you have a shift in this graph? This purple graph is now the new graph with a higher temperature. So this graph is actually shifted to the right compared to the red graph, which tells you that the temperature or the kinetic energy increase for all of the molecules in the reaction. Whether the molecules will take part in the reaction or not, the temperature or the kinetic energy will be higher. So if you increase the temperature, all molecules will have a higher kinetic energy. That's why the whole graph shifts to the right compared to the red one. Now, all of them shift to the right, but all of them will still not take part in the reaction because you will need a very high amount of kinetic energy to take part in the reaction. But because you increase temperature, now wherever the activation energy is, this graph here will be higher up. So this purple graph is now higher up because of the higher temperature, which means that the area under this graph is now much higher. It's going to be the green part and the blue part together, which means now this area has increased a lot. So because the area increased a lot, it means more molecules now are going to take part in the reaction, because more molecules now have kinetic energy, which is higher than the activation energy. So if you increase the temperature of a reaction, the whole entire molecules or reactants in that reaction will have higher kinetic energy, but the ones that will take part in the reaction will be more, and you will get a graph which is higher than the original graph. So this area under the graph will be more. Okay, so that is how temperature affects the Maxwell-Boltzmann distribution curve. It basically gives you higher area or greater area under the graph where molecules will take part in the reaction.